Okay, it's just about 2 o'clock, so we should probably make a start to this session. So welcome back to the SIXNet workshop for the third session. The first presentation this afternoon will be given by Thomas Schmidt. He currently works for HAW Hamburg, although he was for many years the computer center manager at FHTW in Berlin. He still works for FHTW in the capacity as a project manager and has done a great deal of research into the areas of multicast mobility. His presentation is entitled Performance Analysis of Multicast Mobility in HMIP Proxy Environment. So, Thomas, over to you.
It's a bit. Good afternoon, and thanks for the introduction. What I'm trying to present here is some view on multicast mobility in the MIP v6 area, and this is joint work with Matthias, who is also here. Yeah. So we heard today that mobile IPv6 has even got an RFC number. It is about ready, and the question is what comes next, what will happen now. And well, what one can expect is that we will see more or less devices on vacation, devices somewhere with home addresses, and we also may see at first in local subnets roaming just workspace, just notebooks, but what we can expect is that there will be some improvements already announced in your talk, yeah. We also have the issue with the 3G mobile operators that want to operate IP, and well, what we might expect is video and voice conferencing once in a while in a mobile scenario, and then we have real-time mobility requirements and also the question of group communication by multicast. So what is the agenda? After an introduction of the mobility and the multicast problem, I will introduce the two current proposals to you, and then I'll come to the performance analysis and finally to some conclusions. Well, we all know the mobile IPv6, and this is a beautiful example of the IPv6 architecture, but the basic problem, it was already mentioned, the basic problem in real-time scenarios is that the mobile node, as it moves, has to do binding updates with the correspondent node and the home agent, and they may be far away, so that may take a long time. So there are actually two approaches to improve performance, handover performance in mobility, and the one is the idea of the hierarchical mobile IPv6, which brings up the proxy home agent called mobility anchor point, producing such a micro-mobility area where handovers are totally hidden. If you want to perform a handover between map areas, you still have to do binding updates with the home agent and correspondent node. But this can be the timing can be covered by establishing a forwarding channel from the old map to the new map. This is the proxy approach, and the other approach is the fast mobile IPv6, which was already mentioned this morning. Basically, it's performed at the access routers and the mobile node as it moves. One wants to predict or tries to predict where it moves to, and then there will be a negotiation between the access routers, and traffic will be forwarded eventually to the new position, and as the mobile node moves over, it will receive the traffic, and forwarding will take place until the binding updates are completed. This is just a unicast case, and what about the multicast problem or the multicast thing? First of all, if we look at conferencing, we have the situation that we basically need a bidirectional multicast functionality, meaning source and reception. And There's some things to know. One is that multicast applications usually are source address aware, as is the routing. And problem with multicast routing is, of course, that it is slow, and that you have, depending whether you're a listener or a sender, you have more or less may have long times. It depends on the routing protocol, of course. May have long times to update trees, source or shared trees, depending on the routing protocol. And the question is, how can we bridge this gap? I mean, you don't want the conference to be off for seconds or minutes. Yeah, this is the first question: how can we bridge this gap? And the second, of course, always is one wants to remain in the unicast mobility infrastructure, which is might emerge now. But there are basically three principal approaches. The one is the bidirectional tunneling, which is in the mobile IPv6 RFC to come. And the point here is the mobile node establishes a bidirectional tunnel to the home agent, and all mobility is hidden as the home agent doesn't move. So multicasting works there, but it is a inefficient triangular routing depending on where the home agent is. Second approach is the remote subscription approach. That means a mobile node, wherever it is, does a local remote subscription, leaving all movement to the multicast routing. And this is essentially immobile in the sense of session handover as you change your address here. And there's, of course, the third compromise approach, which is agent-based. You have the situation that there's some agent covering multicast handling for a mobile node. And there are many suggestions in the literature and many theory on how to do this. From the draft point of view, there are two drafts. The one is linking with a fast mobile IPv6. This is the fast multicast protocol for IPv6, and this is the approach is let's say agent-supported remote subscription approach. It's not a pure remote subscription approach. It is only for receivers, and it is built on this FMIP procedure. That means it predicts handovers on the layer 2, layer 3 topology map, and it is handled at the access route is similar to the fast mobile IPv6. And there's an extension of the FMIPv6 signaling by a multicast address option. And the way it works is visualized here. You, as a mobile node, are at the previous access router, and you predict your handover and send a fast binding update. The two routers start their dialogue. Whoops. Eventually, they start forwarding and also do the remote subscription. The traffic, and then the mobile node hands over, receives the forwarded traffic, multicast traffic here, and once in a while the remote subscription will bring the real multicast stream to the mobile node, and the procedure is over. Second approach is based on the HMIP, on the hierarchical MIPv6. It does use this map. Construct the mobility anchor points as a multicast agent. It is meant for multicast reception receivers and sources. And what it does is, in analogy to the HMIPv6, it hides all micro-mobile handover. It performs a reactive, not a predictive handover, as the HMIPv6 is also reactive. And the mobile node is addicted to the map and may receive the multicast traffic by forwarding. There's also a signaling extension for the multicast advertisement. Well, there are two, as the problem is asymmetric, there are two views to take. The one is the position of the multicast listener. Here the mobile node is connected hooked to the map, and the map is handling the group membership for the mobile node, and on the handover, the packet forwarding, the mobile node performs an update, and the packet forwarding is done through the old map, through the previous map. For the sender, well, there's one extension as multicast applications are source address aware. You don't want to change your source address, so you should use the home address destination option. And on the handover, you bypass the traffic as a mobile source to both maps, the old and the previous. And once in a while, the handover is performed. There I have also a couple of pictures. Here are the two map domains and the mobile node. In the first map domain sends multicast traffic through the map, thus performs a micro-mobile handover, which is invisible to multicast routing. Then, once in a while, it will perform a handover in the map from one map domain to the other, bypassing the traffic through both channels, and eventually, the multicast routing will have adapted to the new situation, and the bycasting is terminated. So now the question is on the analysis. What are the properties? What are the features of the two approaches? And the first question is what should we analyze? There's of course the question of handover performance, especially the question of packet loss. How long does it take? How many packets are lost? Question of performed handovers. How many handovers are needed? How many handovers are performed or even processed without performing a handover? This is only true for the predictive case. In case there are situations where you predict a handover but you don't perform it. Also, a question is the robustness of the approaches. Is it sensitive to topological things, or how does it survive a rapid movement? And also an efficiency question is signaling overhead. Well, first step is first look at the handover performance. There's we made a simple analytical model, and there's also simulation in a second. What we did is, for simplicity, we assumed a simple handover from, we identified map and X router in this case to make it comparable, and we made a simple handover in a topology, which is we call it step size here, which is of a link distance for the link L3. And the characteristic problem, of course, is this link distance here, or the time it is needed to communicate via this link. And then you have, if you do some calculations, look at it, you have basically for the predictive handover the situation that your off time is proportional to the absolute value of 2 times back and forth communication, this link distance, and minus, because it's a predictive handover, minus the layer 2 time in a situation where these fit nicely together. You have the optimal performance of the fast MIP, and in the reactive handover, you have the situation of needing both the communication once via the link 3 and the layer 2 handover. So we made some simulations. Well, here's some parameters. We injected a probe on the simulated. It's a computer simulation. It's not a true network, but we simulated a probe, sending probe packets every 10 milliseconds. And we fixed some parameters which are sort of characteristic. This we measured the layer 2 handover in a previous experiments with a mean of 50 milliseconds and then fluctuation of 10 on the scale of 10 milliseconds. The anticipation time is a bit hard to guess, so we fix it in a similar range, and the local link is of course is small. The time is small. What do we see? We have curves. On the x-axis, we have the router distance, this L3. The question, how far are the routers? And this number of packet losses corresponds to 1 packet to 10 milliseconds. And what we see is that the predictive handover goes down as to its minimum, which is about at this situation where the router distance is about half the layer 2 handover. We see that the reactive handover more or less grows. Well, there's one, so it looks, well, it goes up here again, but it looks very nice. There's one thing that you have a finite probability to complete the prediction, and this probability decreases as the router distance, as the communication via the neighboring router's parent NAR gets longer. And this looks like this. It's the same scale here. So if the routers are close, you have a very high probability of completing the communication, the prediction communication. And if the router distance is further, you have no probability at all. So next question is the question of the number of handovers. It is sort of obvious that the handover in a fast MIP environment is the number of handovers is more, since it is performed at the access routers, and in the hierarchical mobile IPv6 it is less, because a map usually accounts for a couple of access routers, and the question is how do they behave, how is it quantitatively? Well, the question is, what are the relevant quantities? Well, one is the ratio of access routers to map, meaning one map serves for how many access routers. There are two other quantities. One is the cell residence time, meaning how is the movement of the mobile node, and the other one is the call holding time, meaning you have a session, voice or video session, and how is the likelihood that you survive, or that your call survives a cell residence. Yeah, and we did well. We picked up a model which is well, sort of common but not very realistic in the mobile phone area. This is the assumption that those two times are exponentially distributed with an open parameter. This has well, it has two advantages. First, it is easy, and second, it is homogeneous, meaning that this distribution is homogeneous, meaning that you're well, you have a different scaling here depending on your access router to map ratio, and the shape of the distribution doesn't change, so you can compare. Yeah, what is this can be calculated analytically. Well, you have a ratio of access routers to map, which is written here on this scale, and you have a second quantity which is formed of the former quantities. This is the ratio of the cell residence time over the call holding time. Meaning, if this becomes small, you are in a very mobile environment, meaning a lot of handovers occur. Whereas if this gets large, you have little handovers, low handover probability. So this is the area of the high handover probability, and this is the area of the fast MIP. This is a NAR to map ratio of 1, and as you go to higher values here, you are less mobile, and you have less routers involved in handovers. So this is an analytical expression of this plot. What you see is you have a pole at the zeros. So meaning that the probability for handovers in a very mobile environment, or the number of handovers in a very mobile environment with the fast MIP or the fast MIP approach gets very high. Otherwise, you're low. Yeah. Third question is the overprediction of handovers. In the beginning, I told you, or you already knew, that you have a certain probability of predicting a handover but not performing it in the fast MIP approach. And to find this out, well, at least we couldn't do this analytically. So we started a simulation, and this is still ongoing. So there's only first results. But the way we do it is we take for the geometry we take these honeycombs, and we draw a circle around them, which is basically accounts for the field of accessibility, and the overlap regions are the predictive areas. I mean, if you travel from here to there, you're in the predictive area. This is the area where you can predict a handover. And what we use for the mobility model is a random waypoint model, but without borders. Well, later on we will compare with a standard random waypoint model, but the standard random waypoint model is usually used for ad hoc networks and on a very finite areal, whereas in this case we don't see border effects to be important. Yeah, the waypoint model just you start at some point and you choose a random direction and you start walking, and the time you walk or the length of your walk depends on this call holding time, which comes from an exponential distribution. We took parameters reflecting a pedestrian walk in this case, and we found something this is not really finished now. This is only a first number. We found something that we had something of 20% of predictions that were not performed. Question of robustness. One question is, do those approaches depend on the location of the home agent or the correspondent node or some other topology? And this is in both cases not the case. They are only local. They are only dependent on the performance or the location of the access routers or the maps. Rapid movement robustness differs here. In the fast MIP approach, you have the situation that you're forwarding from the previous access router to the next access router is combined with signaling, and if this is not completed, while you do your next handover, you get in trouble. Your forwarding will probably not work. In the HMIP approach, you stick, the way it's done is you stick to the established map until you completed a handover. So what happens that the delay increases of the forwarding, but you're robust on frequent handovers. Well, the last, so I'm in time. The last is the question of signaling overhead, which is easily, you just can count both approaches, have an advertisement, which is comparable. And in the FMIP approach, you have 7 messages to pass to complete the handover, plus the signaling of MIPv6 and the multicast routing, if any. And in the hierarchical MIP approach, you have, if you're in the micro mobile area, you have 1 update message and no MIPv6 or multicast routing. And if you do an intermap handover, you have 2 messages to pass, and of course, in MIP and multicast signaling. So to conclude, well, there are 2. I tried to introduce the 2 approaches, and what we see from the analysis is that the fast mobile IPv6 approach is faster, especially at intermediate router distances. If the distance gets large, the probability piece. Problem or the situation with the FMIP is that it has a sort of nervous routing demands. By any prediction produces remote subscription, and it also will fail on rapid movement. The HMIP approach is slower, but still compatible in timing, and it reduces the number of handovers at all, and it sort of behaves like smoothing it behaves smooth to the multicast routing. Well, it's probably more loved by multicast routers. Yeah, what we will do in future is complete some of the analysis and to maybe come up with some ideas of refinement. Thank you.
Okay, so that's perfect timing. So we do have time for some questions, if there are any. Yes, Demetrius.
It's marginal adoption. That mobile multicast can survive with regard to, let's say, a mobile and application of the multicast. We believe that multicast on mobility can survive against application-based multicast on IPv6.
You mean this is a political question, or?
Yes, really political, but it could be technical too. You know. I mean, I saw the issues that have to be resolved in, let's say, in the native multicast approach, which might not be the case with, let's say, applications that are multicast.
You mean overlay multicast from the well, from the political point of view, I mean, it is well, there are situations where you don't have overlay networks, so there is a reason for having multicast support in the original multicast support in the network, well, otherwise, I don't know. I mean,
yes, I know it's quite advanced. I mean, the mobility and multicast is quite advanced issue, but do you believe that this kind of functionality would really be established in real networks?
Well, I believe that I mean, there are situations where you need this multicast. I mean, this true multicast routing. I mean, where you don't have an overlay network, or where you can't simulate it by ncast, by n times multicast. So I believe it is worth trying to bring it to life. I mean, and otherwise the market will decide. I don't know.
Okay, any further questions? Okay, so thank you again. Okay, our next presentation is on IPv6 security with respect to firewalls. This will be given by János Mahási, who is a senior network engineer who works for HungerNet in Hungary, of course. HungerNet is a Hungarian national research network. János has also worked previously in the Géant network and has participates in the 6net project.
Thank you very much. Good afternoon. I will speak about the IPv6 security, mostly from point of view of the firewalls. What will be the outline of the presentation? First, I will discuss the requirements of the IPv6 firewalls, then the different kind of firewall architectures possible, then how the firewalls and addressing should be addressed, how it should be done, then some application support that is missing and should be there in the firewalls, especially in the IPv6 firewalls, and then major work about the survey about the available IPv6 firewalls, and then some future work. We are speaking about the IPv6 that is better, it can have better security. But is it really true, or just we are speaking about the better security? We are speaking about the IPsec, but we can see that it's quite difficult to deploy IPsec in a real environment, in a large scale especially. What makes difficult IPv6 security? There is a big remark that the design of the IPv6 made that there is no need to network address translation, and then that makes the security people a bit nervous because they are like to put the networks behind the net, and they solve the problem virtually, but it's not really true. What about the scanning? That is the basic idea of IPv6, or not IPv6, but IP intrusion. We can say that with IPv6 it's virtually not possible because we have 2^64 address range that we have to scan to be able to detect hosts. But of course, there are some clever can have some clever method, especially if the end user administrators are assigning addresses by incrementally or some predictable pattern. To prevent even further the scanning, we can deny the DNS zone transfer. Of course, we can make it more secure using DNS splitting setup. What is wrong with the IPv4 world, that net doesn't make that doesn't hidden the inherent, it doesn't make hidden the problem of the IP network. So the net can help some form, but a really good firewall can also provide similar support. What is problematical also in IPv6 firewalls, we need support for header chaining. We need support for transition and coexistence. And what is more important in IPv6 security, we shouldn't break with our transition tools and our IPv6 devices that we are putting in our network, we shouldn't break the IPv4 security if we want to really deploy IPv6. So, what kind of model can we set up? This is the basic setup. We have the internet, we have the router, firewall, DMZ zone, and also we have the protected network. What is the advantages and what is the disadvantages of this architecture? If we are relying on the neighbor discovery in this network between the router, between the firewall, or we have a self-breacher or bridging firewall, different kind of marketing term for kind of layer 2 firewalling. Then between router and the protected network, we should have some kind of recognition in the firewall. So firewall must support neighbor discovery and neighbor advertisement, and should be able to filter that one. If we are relying also on the auto configuration, the stateless address auto configuration from that router, the firewall must support router solicitation, router advertisement. So that is also a requirement for the firewall if we are using this kind of setup. And also we are using multicast, and we are relying on that router also for multicast setup. Firewall must support multicast listener discovery messages. The other, it's also quite widely used, that we have a firewall right at the internet endpoint, and then there is a router inside. Maybe there are some combination also, more than one firewall, here another one. Here also we have to have support the neighbor discovery messages. What is more challenging for such a setup, that firewall must support filtering dynamic routing protocols. Here you might have to able to filter BGP messages, OSPF messages. That is quite can be quite challenging, especially in IPv6 environment where OSPF version 3 security should be supported with IPsec. So if we are using IPsec here, it's really challenging for such a setup. And also if we are using such a setup, because the internet connection can be quite different from E1 to gigabit Ethernet, let's say, the firewall should support different kind of interfaces. The third method that is quite popular in the small office, home office environment somehow combines the problem of both worlds. Means usually should support everything that router and firewall should support. So MLB filtering, router advertisement filtering if we are relying something outside, or just here it depends on how internally develop the software to be able to send router advertisement to the end hosts. If we are using, of course, stateless auto configuration. So after the requirements analysis, how can we set up our firewall? It's basically this work is done in part of the SIX network, and we wanted to deploy IPv6 in campuses. And at the campus networks, the firewall is one of the building blocks, usually at the edge of the network, and the administrator of the network, the campus network, wanted to know how to set up the network to able to filter the IPv6 packets. So what we have comparing the IPv4 world. Of course, it's very useful to have support echo request and reply because we can much easily debug the programs. We have some other messages comparing the IPv4 world that can be quite useful. We have a number of IPv6 specific ICMP messages. We have parameter problem, as I mentioned, neighbor solicitation, neighbor advertisement, router solicitation, router advertisement, and what is more important, the packet too big messages. Because this is part of the pass MTU discovery, if we are discovering silently these pass MTU discovery messages, then you can create some kind of black hole that is usually very common in the ADSL world. Because in the ADSL world, they are forget to set up the MTU, the correct MTU, and then the end user cannot really identify the problem. Just a certain part of the internet is not reachable. This is also it also can happen with IPv6 if we are not enabling packet too big messages via the firewall. Then the multicast listener discovery. What is also a common accepted method in IPv4 world to completely remove the packets that has IPv4 options. What can we do with extension headers? We have lots of different kind of extension headers. We have hop by hop header, for example, with jumbogram or router alert option. I'm not quite sure, but probably we can log them and just silently discard them. With routing header, it's a kind of problematical thing it's used mainly for source routing and also for mobile IPv6. If we are in IPv4 world, it is considered harmful, but it's required for IPv6 mobile. There are different options if we are using or don't using IPv6. Mobile IP. ESPN authentication header. We should process them according to security policy. So either we are supporting IPsec, then we should allow. If we are not, we should drop them. Fragment header. There are not much wise thing that we can do with fragmentation, because fragmentation is allowed only at the end station. The firewall is not the end station at all. So we can somehow detect whether is some malicious packets are coming, but not much. What is written in the specification, the IPv6 specification, that all but last fragments should be bigger than 1240 bytes. What about the best current practice, the RFC 2827 ingress filtering? We can say it is same. We should apply them for IPv6. It can be a bit easier because the address is hierarchical, so we cannot really expect different kind of addresses from ingress points. Then, so it can be a bit easier. And also here we can make a big progress because almost all platforms can support ingress filtering quite easily with unicast RPF check. What about the broadcast amplification that is problematical, like the Smurf attack? The ICMP ICMP-v6 RFC explicitly disallow replying with multicast source address. So this shouldn't be a real problem. As I mentioned, the IPsec can be problematical if we are using architecture too. What about the addresses? There are two kinds of addresses currently, and we will have soon, I don't know when, a kind of site local address, but we will call them globally unique local addresses. So I think that can be challenging also if we are using them and we are not completely protecting the border of the internal departments. So that can be problematical. What can be the general rule for IPv6 firewalling? For local addresses, I can say that we can mostly allow the communication because it's only link local address. So there is no possible way to get out of the router. And according to the security policy, we should filter the global addresses. What about in case of abuse? What can we do? How can we do some analysis? If we are using stateless auto configuration, one possible traceback available. We have the IP address that contains the interface ID. Then we can translate back the MAC address. If we are not using the privacy extension. Probably if a security people is managing a network, it doesn't allow privacy extension. Because otherwise they cannot really trace back who was the abuser. That is a real challenge for the administrator to prevent that one. Because some firewalls, especially the NetFilter, can provide some service for that one. firewall could break the global connection if the interface ID and the MAC address is not really matching. Of course, if you are setting up static addresses, you have to be careful with filtering. What about if we are using DHCP-v6? We can trace back the information who are using which addresses. But are you sure that you have the DHCP-v database for last Monday 2 a.m. when usually the breaks are happen? So it's really, we have to have a real DHCP-v6 database to be able to trace back the abuse. And also, what is important here, especially in the Cisco switch environment, but some other vendors also have service for that one, in the ARP spoofing or ARP inspection in their switches. That is no such a service available currently for IPv6. So that has to be improved, I think. So the firewalls or switches should be able to detect inconsistent neighbor discovery cache or MAC changes that can be problematical in a campus environment. What about the applications? The most problematical one that we have faced currently, not mentioning the H323, the FTP. The FTP protocol is very complex, specifying the port, whether you are using passive or active mode. You have different kinds of command. Port, L port, E port, PSV, LPSV, EPSV, different kind of FTP commands. And if your firewall should support them and handle them correctly, it's really a challenge for the firewalls. And as we found, virtually no support in IPv6 firewalls for that one. And somehow our view that the next generation file transfer protocol will be the HTTP with WebDAV and Delta extension, because it's really much easier to do some filtering on them. Going to the evaluation of the different kind of firewalls. We evaluated the mostly the freely available and the firewalls that is used in campus environment. The IP filter 4.1. We can say that there are some good points and problematical things. The most problematical thing that the ICMP-v6 support is quite vague, I would say. They can support router solicitation and router advertisement pair, neighbor solicitation and neighbor advertisement pair, but in a quite limited way. So they expect for each router solicitation and router advertisement message. What about if we have router advertisement periodically? So it can be problematical. There is no FTP proxy support, but otherwise it's quite complete one. There are some quite nice features, and what we found that the performance degradation is quite acceptable. We did a small test. We have a tester and a server. The server system was a FreeBSD 4.10 pre-release, and we tuned only the max users to 2024, and we are used tiny throttle turbo HTTP server, the THTTPD, for performance reason to be able to test here that is applied a kind of personal firewall on that server. And we are used for testing a Linux environment that was quite heavily tuned. We had to make some modification to able to open a number of open files, and we used Apache Bench for somehow test the performance of the firewall. What we have tested, we wanted to test the difference if we are enabling firewalling here at that point, that choke point, in a stateful stateful firewalling. So only the stateful filtering was important, because otherwise the UDP, it shouldn't be a real difference, just some kind of minimal delay. What we found, we run 1,000 times different number of concurrent requests, up to 10,000 with 100 byte requests and some other different kind of requests. But just the 100 bytes and the 1,060 bytes are presented here. So you can see there is no real difference. There are some delay, but not much, less than 10%. If we are going up to the 1,060 bytes, it somehow makes it worse, the situation. But still, I would say that it's still quite acceptable, because the firewall should be able to should copy 2 times the packets. So it's still, I would say, it's still okay. With less packets than one Ethernet frame, it's almost the same as before. What about the PF that is developed for the OpenBSD? That we found that the problematical thing that the fragmentation headers are not really handled at all. That means all the fragment headers are blocked. I am not quite sure that it's the right solution. Sorry, if you have an IPv6 packet with fragmentation header, then it's dropped. Probably it's not the right solution, as I mentioned. As earlier, because it's basically the ideas came from the IP filter. There is no FTP proxy support for IPv6, but there are some very nice features. The ICMP-v6 support is almost complete. All the ICMP-v6 error codes can be specified numerically and symbolically, and we can have TCP sequence, IP-ID randomization, and also we can have QoS. What about the other IPv6, other firewall in the BSD systems, the IP6FW? I would say that architecture is not too modern. It's not a stateful firewall, except the IPv2, that is the next generation of the earlier, the IPv4 version, that has also some extension for stateful filtering. No proxy support at all. The anti-spoofing setup quite problematical. That means you have to think it over what kind of packets you want to allow, but otherwise you can do it. With IPFW2, that is kind of a next generation of the IPFW, it's just one switching on one flag. What is good anyway in that firewall? That there are some predefined rules in each BSD system that has the IP6FW. So you can tailor your configuration quite easily to your setup. What about the Linux world? NetFilter has quite good filtering capabilities, quite weak the portability, it's only in the development version, the development is not really contain all the patches. If somebody is working with NetFilter, you might be familiar with the Patchomatic and Patchomatic NG that allows you to enable different kind of feature sets for NetFilter. In the development, the current version doesn't contain, the current development version doesn't contain all the IPv6 features. Especially, there is no support for connection tracking. In NetFilter, there is recently a connection tracking extension for IPv6. That means the current version is only stateless filtering allowed. Otherwise, it has a quite complete filtering capabilities of the NetFilter. What else is important? Cisco access lists. Quite good filtering capabilities. What we found, the current thief train from Cisco. There are two sets of Cisco access lists, standard ACL and extended ACL. What is problematical, I think, it can filter only the next header value. If we want to filter inside the next header to see what's inside the next header, it's impossible with the current access list. The traffic class can contain only 6 bits. It's kind of limitation instead of 8 bit that is available. And one of the biggest problem, if we want to use the best current practice for ingress filtering, the unicast RTF check is not universally available in each Cisco platform. But otherwise, it's a very good platform for firewalling because you can have also stateful firewalling with reflexive ACL, also with IPv6. And one interesting feature is the implicit deny. If you don't configure anything that has an implicit deny, that also contains the neighbor discovery messages to go in and out. That is, can be quite challenging if you are configuring the access control list. What about the Juniper firewall? It has rather good filtering capabilities. It also can filter only the next header value. And what is the biggest problem in the Juniper firewall, the current implementation that we are testing, the Junos 6.2, that you cannot match the TCP flags in IPv6 filters. So you cannot see whether it's a connection establishment or you have already have some information, the previous packets, or you want to finish your connection. So there are some problems that has to be improved. The good points that we couldn't find any performance impact if we are enabling IPv6 firewalling. What about the conclusion? We can say that we can safely enable IPv6 firewalls because they are have quite good broad existence of the IPv6 firewalls. They are rather usable. They can be used for firewalling IPv6 network. Also, we can have commercial support from different vendors like Cisco or Juniper. The transition aspects we haven't really investigated yet, but we have to do it. And there was some work, and we are doing some ongoing work on the 6 network package too. And as I mentioned, the mobile IPv6, if we are really tight in security, it can be some problematical thing. Okay, thank you very much.
Thank you, Janos. Is there any questions?
I'm wondering about the IPv4 compatible and IPv4 MAC addresses. Are they of any concern for firewall setups?
You can easily filter them if you want, because it's easy to filter by the address match. So if you want to filter them, it's easy to do. If you want to look inside the tunnel packets, it's really impossible any of these firewalls. So if you have to look at the tunneled packets, you are out of look.
I mean, for example, if people forget to include these addresses in their firewall setup, can they use some kind of threat?
It depends on your setup. If you start from the denial setup and you allow what you need, it shouldn't be any problem. If you do the other way around, that means you filter what you don't like. Probably you have to filter such addresses also.
I'm not sure whether I understood, but you mentioned the Juniper filtering and that you could see TCP flags and stuff. Is it true that you can't, then you shouldn't see the TCP ports and UDP ports? Is that right? Or?
You can see the TCP and UDP ports, but not the TCP flags. Probably just because they haven't implemented yet. Because I asked this one from Juniper, and they told me that they will implement it when they have time.
Not sure if I understood, but you said something about discarding broker other options. For instance, for MLD positions, it's important to have the other option. That's not the reason to get confused and don't feel.
We have to continue the investigation. So. Okay. Yes.
I don't know if you have examples of firewall configurations.
Some short examples you can provide if you want. But we are doing in the 6 network. There will be a deliverable IPv6 security toolbook also. That we are working together with GRNet, and there will contain lots of material of this one and lots of examples for setting up firewalls. Yeah, a kind of cookbook how to do that one and that one. The idea of distributed firewalls can be good, but as I discussed with the manager of the campus networks, they are not really like such an idea. If they want, the distributed firewall can be good if you can somehow make a virtual firewall somewhere and make it available for configurable for certain people, but only one administrator mentioned that can be useful for them, but only one, and 10 others are completely against such an idea.
Okay, I think we'll have to leave it there. we have one more presentation today. This is an investigation of quality of service mechanisms for supporting SLAs in IPv6. This will be given by Vasilios Siris, who is an assistant professor at the University of Crete, and he's also a researcher at the Greek Foundation for Research and Technology, is it? I know it as FORTH, but I can't always remember exactly what it stands for. Anyway, I'll hand over to Vasilios.
Thank you. Good afternoon, everyone. So as the title of my talk suggests, what I'll be presenting is the results from our investigations of quality of service mechanisms in an IPv6 testbed, mainly from the perspective of supporting service level agreements between a provider and a customer network. So the objectives are to investigate the quality of service mechanisms, as I said before, and more specifically, policing, shaping, and queuing. The reason why this is interesting and important is because these mechanisms will be used at the interface between a provider and a customer. Hence, their tuning is very important for effectively supporting SLAs. And also, investigating each mechanism in isolation is not sufficient to provide us for guidance on how this tuning should be performed. And also, another motivation for our work is because this work is in particular for IPv6, and because we have also done similar investigations with IPv4, a question that arose to us is there any difference between IPv6 and IPv4? So, as I said, our interest is in the customer-provider interface. So, this is exactly the interface I'm referring to, and this is the provider edge or border routing, and this is correspondingly the customer edge routing. And the mechanisms that I'm referring to are shaping and class-based queuing, which can be applied at the output interface that connects the customer's edge router to the provider. And then from the provider side, we have policing. There must be a way to check that the customer is sending the traffic that is indicated in his SLA. And also, he might use class-based queuing at the other side of his router to provide a different share of bandwidth to different customers. And mainly the investigations that I'll be presenting refer to traffic flowing from the customer to the provider. And in particular, the mechanisms that we investigated are the following. First of all, we considered both Cisco and Linux software-based routers. And in terms of the Cisco router, we considered Cisco's traffic policing. That's the name of the mechanism, since CAR is not supported in IPv6. And in terms of shaping, we considered Cisco's generic traffic shaping. And then in terms of the Linux router, we considered the traffic policing, traffic shaping mechanisms, both of which, and indeed Cisco's corresponding mechanisms, are based on this the token bucket filter mechanism. And also, for Linux, we considered class-based queuing. So just a quick reminder of this token bucket mechanism. At least in theory, this mechanism works as follows. We have a bucket here which fills at some particular rate. The bucket has some maximum size which it can accept tokens, and if that fills up, tokens are just dropped. And for each packet that is arriving, a check is performed to determine whether the amount of tokens are enough or more than the arriving packet's length. And if that is the case, then the packet is forwarded. If it's not, then it's dropped. If we have a shaper, then we additionally have a buffer which temporarily queues the packets which don't pass this check here. Now that's in theory, because in practice, implementation differs. And actually, from our understanding, what is implemented in both Cisco and Linux machines is, let's say, a more discrete time version of what I just described. And hence, there is a time interval, and within this time interval, there's a maximum amount of traffic that the user is allowed to send, and this maximum amount of traffic is given by this committed burst size. And if you divide this committed burst size by the time interval, you get the committed information rate, which is the corresponding rate. So in the, as I said, we consider both 6-scope Linux-based routers. The end systems run Red Hat Linux. For the first part of the results that I'll be presenting, we consider TCP traffic generated by Ampere. And also, all these machines are in a local environment in the lab. Hence, the round-trip time corresponds to such distances. Now, the first test, as I said, we want to investigate this interaction of mechanisms. But we'll start simple. Consider one mechanism. And at least what a provider must have as far as its side is concerned, it must somehow police the traffic that the customer is sending to check whether it conforms to the SLA. So we first consider only policing, as I said, at the provider side, which is basically the right route that is shown here. And traffic is flowing, as I said, we consider mainly TCP traffic, at least for these tests. TCP traffic is flowing from the customer side, which is the left here, towards the right, which is the provider side. And what we do with this test is we fix a policing rate. So we have a fixed policing rate. And what we do is we measure the aggregate throughput that is achieved by this user, the total TCP throughput, for different burst sizes. So that's the experiment. Hence, the graph that I show here, as I said, is for a fixed policing rate, and indeed, these different colors here correspond to a different policing rate. And this vertical axis here, horizontal, is the burst size. So we change the burst size. And as one would expect, that increasing the burst size increases the aggregate throughput, which is shown in this axis here. And the other thing that you might notice is that as we move from the lower curves here to the higher curves here, we have a higher policing rate. For example, this blue line here corresponds to 10 megabits per second, whereas this brown line here corresponds to 70 megabits per second. So that's one observation, that as we increase the burst size, we increase the aggregate throughput. But the increase is not the same for every increase of the burst size. After some point, somehow the increase is much more smaller. And that's why these curves, after some value of the burst size, tend to be flat. And that's one observation. The other observation is, for example, take this blue line here, which, as I said, corresponds to 10 megabits per second. Now, the aggregate throughput is almost 10 megabits. It's 9 point something. That's very close. Whereas if we go to a very higher policing rate, 70 megabits per second, that's a brown line here. Well, from the 70, we can only achieve 45. So as we increase the policing rate, we can somehow utilize proportionally less the rate that is allowed by the police, by the policing rate at the police. And that's what I note here. As I said, the throughput increases with the burst size, but is obviously always less than the policing rate. And the proportionally smaller utilization as we increase the policing rate. And also, we had virtually the same, at least qualitative results between Cisco and Linux routers as the ones I just showed. And also, one can, because I mentioned this dependence, after some point there's a much smaller increase of the aggregate throughput. That means that there's somehow a need for some burst size, after which it doesn't, we don't gain much by increasing the burst size. And at least for the experiments that we conducted, one can suggest a heuristic, let's say, way of calculating what this optimal burst size, which is, as I said before, the location of this knee, for which we don't gain much further if we further increase the burst size. And these are the numbers here. What's interesting to observe is that it's not sufficient to have a burst size which is larger than the round-trip time multiplied by the rate. We need something more. Okay, and obviously we're talking about TCP, and TCP's congestion control algorithm is obviously affecting these results, and is the main reason that we have what the results that I'm showing. This graph is for different number of flows. So going from the bottom to the top graph, we have an increase in the number of flows. This is for 1 flow. This is for 10 flows. Again, this axis here is the burst size, and the observation here is that this optimal burst parameter that I mentioned, which is where the knee is located, is virtually independent of the number of flows. So that's one of the observation from the previous graph. And also the other observation is that as we increase the number of flows, these curves are higher, meaning that we achieve a higher aggregate throughput. And again, the results that I showed are basically the same if we use either Cisco or Linux routers. Okay, that was for policing. Now, what if we add shaping? So shaping will basically be used at the customer side. So the customer will shape his traffic before he sends it to the network. So the results that I'll be presenting now are for a fixed policer here, meaning fixed burst size, fixed policing rate. And the shaper here has the same rate as the policer here, but we change the burst parameter of this shaper here. And again, what I'm trying to see is what the aggregate throughput is and how it depends on the burst size of this shaper here. And these are the results. Now, the different colors are for a different number of flows. So, for example, this blue line here is for the case of 1 flow. We have the policing and the shaping rate are 50 megabits per second. This is the burst size, as I said, of the shaper. And what we observe here is for a very small burst size value, we have an increase of the shaping rate, of the aggregate throughput, sorry. Then we have somehow, we're able to achieve some maximum value of this, of the rate. And then if we further increase the burst size of the shaper, what we see is a decrease of the aggregate throughput. Now, well, for the blue line, it's not really shown. What the achieved throughput is in the case we don't have shaping is this line here. And for example, this purple line here, the straight line corresponds to the throughput that is achieved if we don't use shaping. Whereas again, this line which increases is what we achieve if we do use shaping. So going back to what I just said, if we increase the burst size very much, then basically we don't gain from shaping. That's what we say here. But if we have the burst size parameter which is in this range, then we actually gain from shaping. And indeed we can achieve very close to the rate, the policing and shaping rate that we have. Again, there is a dependence on the number of flows. This blue line is for 1 flow. Here we have 2 and correspondingly more flows. But there's also, and this is interesting, a dependence on the range of burst size values for which we achieve this maximum value. So that's the interesting thing. And just a quick note, why do we have this dependence in this area here? Well, there the burst size is very small, so essentially we don't allow the TCP algorithm to take advantage of what is being allowed by the provider. And of course, if we have a very large burst size, then that means that there's essentially no shape. Okay? This, I think, more or less, I've said this. Now, of course, you might wonder, well, why don't you just set the burst size of the shaper equal to the burst size of the policer? Well, because that's not always optimal. That's what our results are showing. So the simple rule of use exactly the same parameters that are used in the policer at the shaper is not necessarily the best thing to do. Might work in many areas, but for many cases, but not always the optimal. And as I said, there's a dependence on the range of burst sizes for which we achieve this optimal on the number of flows. And here, I think these results refer to the case where we have shaping policing in Linux workstations. Again, qualitatively, the results that we find are the same as the ones I showed before, which was the case for Cisco routers. So there's no qualitative difference in these results, which consider both policing and shaping together. Now what I do now is instead of having a fixed shaping rate and changing the burst size, I do the opposite. I have a fixed burst size, and then I change the shaping rate of the policer, and I plot the throughput, which is again in this axis, for this different shaping rates. What is interesting here is that, for example, as I said, 50 megabits is the policing rate at the shaper. We still have achieved a maximum throughput if we have a rate higher than the 50 megabits of the policer. But if we increase more the shaping rate, then again we see a decrease in the aggregate throughput, which again is due to the fact that essentially we're not shaping traffic, we're just allowing it to enter the network. So this is what I just explained in reference to the graphs. Now, okay, up to now what I've said is that okay, if you use a shaper, you increase the aggregate throughput. That's one thing I said. I also said that if you have, there's a range of burst sizes for the shaper which achieves this aggregate, increased aggregate throughputs. Now, the next obvious question is, how do you select from these different burst sizes? Well, the answer is, if you're also interested in delay, for example, then you have to add delay in the picture. Up to now, I was investigating and showed the result for aggregate throughput. Now, if you consider delay, then the dependence of the burst size, this is wrong here. This is delay jitter, it should be delay jitter. And the delay jitter dependence on the burst size is this decreasing graph, which is, again, expected. If you increase the burst size, then essentially you're delaying less traffic, and so decreasing both the delay and the delay jitter. So if you, in other words, in order to tune, which, as you might recall, is one of the motivations for this work, how do we tune the parameters of all these mechanisms? If you're interested in both aggregate throughput and delay, you have to consider both. Hence, you have a range of burst sizes which increase the aggregate throughput, and from graphs such as this, you can see the delay jitter, and obviously you want to be toward the right side of this graph. And consideration of both of these parameters can help you, as I said, tune appropriately the parameters. Okay, I'll very, very quickly go through this. The other results that I can show you are for the case that we have class-based tuning at the customer side and policing at the provider side. I won't show the class-based tuning usually is used to somehow provide different amounts of bandwidth to different flows. I won't show the results for that, but because of the other results I showed regarding shaping and policing, I will consider using flash-based tuning as a way also to shape traffic, and that's the results that I consider. And for at least the Linux implementation of flash-based tuning, there's a max burst parameter, which, as we guess, is related to the burst size that is allowed to enter from this router here to this router here. So again, what I'm showing is I'm fixing the parameters of the policer, I'm fixing the rate of the flash-based tuning mechanism, but I'm varying this maximum burst parameter. And what I'm trying to see is what is the aggregate throughput. And this is just for one flow. The aggregate throughput has this dependence here. Now, the main difference between this curve and the corresponding curve where we had the burst size of the shaper is that, well, as before, we have an increase of the throughput, but after some value, in the case of shaping, we also observe a decrease of the throughput. We don't observe a decrease here. And we conjecture that this is due to the fact that this CB2 mechanism, at least its implementation in Linux, is actually smoothing the traffic here. So it's just not shaping the traffic, that it's limiting the packets that are in excess of the policing token bucket at the other side, but it's also smoothing the rate with which it's sending packets, and this is one reason why you don't observe this decrease in the throughput. So that's this is exactly what I said in reference to the previous graphs. So now I'm ready to conclude my talk. Again, the main motivation is to investigate this interaction of various quality of service parameters in an actual IPv6 testbed with having in mind to support effectively SLA between the customer and provider. And some of the results are, well, shaping can be beneficial, it can increase aggregate throughput. One must also have in mind the delay. Hence, both throughput and delay must be considered when tuning these parameters. The other, let's say, initially unexpected, but after you think of it, there might be no reason to observe different behavior between Cisco and Linux routers. Maybe their implementation is very similar. That obviously should be the case. And also another interesting thing, we didn't notice, as I said, we performed these tests with IPv4. We didn't really see any differences between IPv4 and IPv6. I guess I am assuming the same thing. Just a couple of directions for further experimental work. What I showed is for a local test bed and small round time values. Obviously, an interesting investigation is to see if the results differ in a wide area network. And also another interesting area is to consider wireless networks. Wireless networks have very different properties in comparison with a fixed link, and it's obviously interesting to see if all these quality of service mechanisms, again, in terms of supporting SLAs, have the same behavior in a wireless link as they have in a fixed link. So I think that concludes my talk. Thank you for listening.
Okay, we have time for some questions if there are any.
we have is if we have IPv6 thumbed over IPv4, to what extent do the results, the behavior, quality of service mechanisms remain the same? That's something we're interested in. And there are two sides of this. First, what is supported by the provider, by the hardware provider, and then what is supported by the functionality per se of the mechanism.
As a more general question, not directly related to it. So, do you know any router that supports or handles the flow label? Does it flow support on base of the flow label?
Can do an access list on the floor level. That it was part of the design. But to my knowledge, nobody has never used that, so I have no clue.
Now the question is, I mean, there are Cisco routers that are flow-based, and that route flow-based. But usually they use the IPv4.
Yeah, but you can, for example, set an ACR for a specific flow level value.
Okay.
And from there, assign all the packet with the flow level value to a specific chip.
Okay.
Now I have no clue if it's working or not. I'm pretty sure nobody has never tested that.
Okay.
But at least when we did the design for the ACL and all the features, we put the flow level as one of the parameters we can.
In which operating release?
It's iOS 12.3 or T or Meynell. Maybe we have bugs and I will never claim it's working. We need to get some testing.
We'll try it out.
Jan, have you had a question?
I just wanted to make a comment on the last slide, if you can go back.
Sure.
In the last graph, yeah, you have different scale. It might be you have 200 packets.
Yeah. Yes, indeed, I have a different scale. Assuming this is because the value that the maximum burst is measured in terms of packets.
In this measurement, have you exceeded those 2 megabit mean burst size on the posting side, on the receiving side? Because it dropped, I think.
Yes, that's should be a good question. I'm not sure what the packet size is here.
I think those are updated according to NTU on the
So yes, that's an important observation that we must exceed this value in order to see if we have this degradation of throughput. That's right. Good point.
Okay, I think that's all we have time for. So thank you again, Vasilios. That brings us to the end of today's 6net workshop. I would like to thank all the speakers and also for all the people that have attended. However, I would remind you that there is an IPv6 cluster meeting after the coffee break here at 4 o'clock. There's a number of interesting presentations there, so if you haven't had enough of IPv6 today, then there's still more to come. It's now coffee, so please go off and find coffee. But I would say that just a couple of points that tonight, in case you're not aware, that there will be two sets of buses leaving for the hotels. There'll be buses leaving at 5:30. There'll be another set of buses leaving at 6:30. And if you're still here at 7:30, there will be a bus here that will take you directly to the gala dinner if you miss the other two buses. So, just for information. Okay, thank you.